Hello everyone. Today we are going to discuss about the bridge full wave rectifier. Before going to the bridge full wave rectifier, we will see what is full wave rectifier. Okay. In full wave rectifier, both positive off cycle and the negative off cycle are processing to the output. That is, two cycles are generated at the output. If you see the input here, this is the input is AC. Okay, positive off cycle, negative off cycle, positive, negative, and continuously it is going on. It is the input is AC, and this input is given to the full wave rectifier. Okay, we will get the pulsating DC. Okay, both the cycles, positive off cycle, negative off cycle, both the cycles are processing to the output. Both the cycles are processing to the output. So we will get the output waveform is like this. So if we give the input AC to the full wave rectifier, we will get the output like this. Two cycles will be generated here. So these full wave rectifiers are classified into two types: center tapped full wave rectifier and the bridge full wave rectifier. In the last class, we have seen about the center tapped full wave rectifier. Now let's see what is bridge full wave rectifier. Okay, this is the circuit diagram of the bridge full wave rectifier. Bridge full wave rectifier, it is having the four diodes. Okay, diode D1 and diode D2, and it is D3 and it is D4. Are the four diodes are connected in the form of bridge. That's why it is called as bridge rectifier. Okay, in the circuit, if you see, there are three components. One is a transformer and one more is a diode and other one is a load resistance. So this is called as a load resistance. Okay, input we are giving AC and the output here across the load resistance, we will measure the DC. Whatever the output we are getting, that we will measure across this DC. Now let's see what are the components we are using in the circuit. If you see the circuit diagram here, in this first one is a transformer we are using. This transformer is used to step down the voltage. As the DC voltage levels are very small, so that's why we have to decrease the voltage. Okay, initially we will convert high level AC voltage to the low level AC voltage only. This low level AC voltage, we will give it to this circuit and finally we will get the pulsating DC. Okay, this transformer function is to decrease the voltage. That is step down transformer we are using. Now, diode is here we are using diode as a switching purpose, and the diode allows the current only in the one direction. Okay, that's why it is called as a diode is a unidirectional device. And next one is the load resistance here. Load resistance is used to measure the output quantity. Whatever the output we are getting, that we will measure across this load resistance. So this is about the bridge full wave rectifier circuit diagram. Now let's see if we give the positive half cycle to the bridge rectifier, what is the output we are getting? And again, we will, if we give the negative half cycle to the bridge rectifier, what is the output we will get? That we will see one by one. Okay, now first we will apply the positive half cycle. So this is a sine wave. It is having the two cycles, positive half cycle and the negative half cycle. First, we will give the positive half cycle to the bridge rectifier circuit. So I am giving positive half cycle to this circuit. So it is a positive terminal and it is a negative terminal. Here we are giving input is AC. Okay, and that is 230 volts single phase supply. Input is AC. That is how much voltage we are giving, 230 volts. Okay, positive terminal and it is a negative terminal, and here also it is positive terminal and negative terminal. Input is VA. If you see the diodes here, it is D1, D2, D3, and it is D4. So we have to take all the diodes in the anti-clockwise direction. So it is a negative terminal and it is a positive terminal. Voltage we will measure across this load resistance, or is a load resistance. Now we'll see which diode is in forward bias and which diode is in reverse bias. That based on the terminal are connected to the diodes. This positive terminal is connected to which diode and which terminal, and this negative terminal is connected to which diode and which terminal. Based on that, we will decide whether how many diodes are in forward bias and how many diodes are in reverse bias in the positive off cycle. Okay, here now let's see this positive terminal of the input. This positive terminal of the input is connected to N terminal of the D2, N of D2, N of D2, and again this positive terminal is connected to P of D1. P of D1. Okay, from this we can say that as the positive terminal is connected to N, diode D2 will be in the reverse bias. And as the positive terminal of the input is connected to P of D1, from this we can say that diode D1 is forward bias. So you know already what is forward bias and what is reverse bias. When the positive terminal is connected to P and the negative is connected to N, then we can say that forward bias. As the positive is connected to P, diode D1 is forward bias. As the positive is connected to N, diode D2 will be in the reverse bias. Okay, now we'll connect the negative terminal here. Negative terminal is connected to which terminals here? Negative terminal is connected to first N of D3. N of D3. And again, the negative terminal is connected to P of D4. P of D4. Okay, here, as the negative is connected to N, diode D3 in forward bias. As the negative is connected to P, so D4 is in reverse bias. Okay, from this we can say that these two diodes, D1 and D3 will be in the forward bias when we give the positive off cycle to this bridge rectifier. Okay, diode D1 and D3 will be in the on position. Now, if you see for the practical diode, when the diode is in forward bias, the total diode will be replaced by the cut-in voltage that is connected in series with the forward resistance. Okay, this condition is when the diode will be in the forward bias condition. Okay, now when the diode will be in the reverse bias, suppose the diode will be in the reverse bias, the total diode will be replaced with the open switch. Now for the given circuit, we will replace these diodes by this equivalent circuit. As the diode D1 and D3 will be in the forward bias, diode D1 and D3 will be replaced with cut-in voltage connected in series with the forward resistance, and diode D2 and D4 will be with open switch. Okay, now if we convert that circuit here, it is a positive off cycle. Okay, it is a plus terminal and then minus terminal, and it is a plus terminal and minus terminal. It is the input VI. Okay, here diode D1, as the diode D1 is in forward bias, the diode D1 is replaced with cut-in voltage that is connected in series with the forward resistance. As the diode D2 will be in the reverse bias, diode D2 will be replaced with open switch. Okay, again diode D3. Yeah, diode D3 is in forward bias. Diode D3 will be replaced with cut-in voltage that is connected in series with the forward resistance. Now diode D4. Diode D4 will be in the reverse bias. That's why we are replacing with diode D4 by open switch. Okay, this is the load resistance. Okay, it is a positive terminal, negative terminal, and the output we will measure across this load resistance. Okay, like this we will replace the diodes with the equivalent circuit. If it is forward bias, cut-in voltage connected in series with the forward resistance, reverse bias, open switch. Okay, now we'll see the remaining circuit of the bridge rectifier. This is V gamma. Okay, this is V gamma RF, and it is a load resistance, positive terminal, negative terminal. It is a V0, and it is a V gamma, and it is RF. Okay, it is input plus and minus input voltage VI. Okay, now if we see the circuit here, it is connected in the form of Z here. Z. Okay, it is connected in the form of Z. Now if we simplify the circuit, okay, I make it straight here. This circuit is connected in the form of Z. This Z I'm simplifying into straight line. Okay, if we will get the circuit like this. Okay, for this we will take the terminals here, plus terminal, minus terminal, and it is the input is AC. Input we are giving is AC, and it is a positive terminal, and it is a negative terminal. Okay, it is a positive terminal and it is a negative terminal. It is input is VI. So it is V gamma and it is RF, and this is called as RL, and it is V gamma and it is RF. Okay, now we will apply the KVL in the circuit here. If we apply the KVL here, if we apply KVL, assume that in this I current is flowing. The next step is apply KVL. Okay, apply KVL. If we apply KVL, what we will get here? Minus 2 place VI first. Okay, after that, place 2 minus V gamma. Again, place 2 minus V gamma is equal to, we will see the voltage drops here. I into RF plus I into RL plus again I into RF. So this is the voltage across load resistance V0. Okay, from this we can say that I is common here. If we take the I is common, we will get I is equal to VI minus 2V gamma divided by 2 into RF plus RL. Assume that it is equation number 1. Okay, now from the circuit we can say that output voltage V0 is equal to I into R. I into which resistance here? RL. Voltage across the load resistance V0 is equal to I into RL. Assume that it is equation number 2. Okay, next step is substitute equation 1 in equation number 2. If we substitute equation 1 in equation number 2, we will get V0 is equal to VI minus 2V gamma divided by 2 into RF plus RL into RL. Okay, in place of I am substituting this equation number 1. We will get the equation like this. Okay, now we have the one condition that in ideal diode, V gamma and RF both are 0. So we have to substitute this condition in this equation. We will get V0 is equal to VI. This V gamma is 0 divided by RF is also 0 divided by RL into RL. This RL get cancelled. V0 is equal to VI we will get. Okay. From this we can say that in the positive off cycle, output voltage is exactly equal to the input voltage. That is V0 is equal to VI. Now, let's see in the negative off cycle. Okay, what are the responses we will get? We will see now. Okay, so for the positive off cycle, what are the waveforms we will get? Now we'll see. So we got the equation V0 is equal to VI. Okay, when the V0 is equal to VI, from this we can say that output is exactly equal to the input. Okay, input is we are giving the AC supply. Okay, output is DC, pulsating DC. Okay, output is exactly equal to the input here. Output is exactly equal to the input. Output is exactly equal to the input for the positive off cycle. We are giving the positive off cycle. If we give the positive off cycle, output is exactly equal to the input. Okay, now this is about the positive off cycle. Now let's see about the negative off cycle. For the negative off cycle, if we give the negative of the input is given to the bridge rectifier, what are the responses we will get? Now we'll see. So we are giving the negative off cycle to the transformer. Okay, it is a negative. If we give the negative off cycle, so the terminals will be reversed here. Negative, positive, and the negative positive. We are giving the input we are giving AC. Input AC we are giving for that too we are giving the negative off cycle. Negative terminal and the positive terminal, negative terminal and the positive terminal. Here terminals will be reversed. If we give the negative off cycle here, this is the input voltage is VI. As we know already that it is a D1, D2, and it is a D3, and it is D4. There are 4 diodes here. Now this is called as load resistance RL, a negative terminal, positive terminal, and it is a output voltage is V0. Now we'll see which diode is in forward bias and which diode is in reverse bias. Same as the previous positive off cycle here. Here negative terminal first. A negative terminal is connected to P of D1. P of D1. Again, this negative terminal is connected to N of D2. N of D2. As the negative terminal is connected to P, diode D1 is in reverse bias. Okay. As a negative terminal is connected to N, diode D2 will be in the forward bias. Okay, this is about the diode D1 and D2. Now let's see about the positive off cycle. Positive terminal. For the positive terminal, if you give the positive terminal to the P of D4, P of D4, and again this positive terminal is connected to N of D3. N of D3. Okay. Here, if the positive terminal is connected to P, so we can say that diode D4 will be in the forward bias. As a positive terminal is connected to N, diode D3 will be in the reverse bias condition. From this, we can say that diode D2 and D4 will be in the forward bias condition for the negative off cycle. Okay. Now, if we replace with the equivalent circuit, as a diode D2 and D4 will be in the forward bias, diode D2 and D4 will be replaced with cut-in voltage that is connected in series with the forward resistance. A cut-in voltage that is connected in series with the forward resistance, and diode D1 and D3 will be in the reverse bias. As a diode D1 and D3 will be in the reverse bias, both the diodes will be replaced by open circuit. Okay, this is called as a load resistance. Okay, it is a positive terminal and negative terminal. It is the output voltage is V0. Okay, for the negative off cycle, for the given circuit, for the bridge circuit, this is the equivalent circuit. Okay, now let's see. This is the circuit we got after if we give the negative off cycle. From this we can say that this is called as a negative terminal. It is a positive terminal. It is the input voltage is Vi. Okay, it is a negative terminal and it is a positive terminal. It is a negative off cycle we are giving. It is the input. Input is AC. Input AC. Okay, input is AC. Here it is called as V gamma, and it is RF, and it is RL plus terminal minus terminal, and it is V0, and it is V gamma, and this is called as RF. Okay, now this circuit, if we make it straight line, we will get the circuit like this. Okay, so this circuit we are converting into straight line here. Okay, as these are open circuited, we are making straight. So if we modify, if we make the straight line, the circuit look like this. Okay, for this, it is a negative off cycle and it is a positive off cycle. Okay, and it is input supply is input is AC. Input is AC. It is a negative terminal and it is a positive terminal. It is a Vi is input. It is called as RF. It is V gamma, and it is RL is a load resistance. It is a this is called as a load resistance. For the load resistance, it is minus, and it is plus. It is V0, and it is forward resistance, and it is V gamma. Okay, apply KVL here. Apply KVL. Apply KVL in the given in this loop. If you apply KVL here, +2 minus VI, and here -2 plus V gamma, -2 plus V gamma. Now we'll see the voltage drops here. I into RF, I into RF plus I into RL, I into RL plus I into RF. Okay, in the given circuit, though if we apply the KVL, we will get the equation like this. From this, if we take the I is common, we will get minus V gamma plus minus Vi plus 2V gamma divided by 2 into RF, 2 into RF plus RL, 2 into RF plus RL we will get. Okay, we know that in ideal case, since in ideal case V gamma and RF is equal to 0 in the ideal condition. Okay, that's why. So before going to that step, now we will apply V0. Voltage across the load resistance V0 is equal to I into RL. This is equation number 2. This is equation number 1. Okay, now we will substitute equation number 1 in 2. Substitute equation 1 in 2. If we substitute, we will get V0 is equal to minus Vi plus 2V gamma divided by 2 into RF plus RL into RL. Okay, as we know that in ideal case, V gamma and RF is equal to 0. So we have to substitute here. Now we will get V0 is equal to minus Vi. In ideal case, V gamma is equal to 0 and the RF is equal to 0. So finally we will get RL divided by RL into RL. RL cancel. So we will get V0 is equal to minus Vi. In the negative half cycle, we will get output voltage is equal to input voltage, but in opposite direction. That is V0 is equal to minus Vi. Now let's see what are how the waveforms we will get in the negative half cycle. For the negative half cycle, so we are getting the equation V0 is equal to minus Vi. Okay, from this we can say that in the negative half cycle, output is exactly equal to the input, but in opposite direction. Okay, this negative indicates the opposite direction. Output is exactly equal to the input, but in opposite direction, because V0 is equal to minus Vi. We will get the output like this for the negative half cycles. Now, if we combine both the positive half cycles and the negative half cycles, okay, assume that it is the input voltage is Vi. Okay, it is a positive half cycle and it is a negative half cycle. It is a positive half cycle, negative half cycle. Here it with respect to omega t here. Okay, so here it is 0, pi, 2 pi, 3 pi, and 4 pi. Assume that it is V0. Here also it is 0, pi, 2 pi, 3 pi, 4 pi, and omega t. Okay, here if you see, for the positive half cycle, output is exactly equal to the input. Negative half cycle, output is exactly equal to the input, but in opposite direction. Here and so on. Here, positive half cycle output is exactly equal to the input, and here for the negative half cycle, output is exactly equal to the input, but in opposite direction. Here, both the cycles will be generated at the output in the bridge rectifier also. Here, in the positive half cycle, diode D1, D3 will be in on position, and D2 and D4 will be in off. In the negative half cycle, diode D2 and D4 will be in the on condition and remaining diodes in off condition for the negative half cycle, and so on for the remaining cycles also. Here D1, D3 in on condition, D2, D4 will be in on condition, D1, D3 in off. So in the positive half cycle, D1, D3 on. In the negative half cycle, D2, D4 is in on condition. Okay, these are the waveforms we will get for the bridge rectifier if we combine both positive half cycle and negative half cycle. From this, we can say that both the cycles will be generated at the output. Okay, now let's see what is the average value and what is the RMS value of the bridge full wave rectifier. Now let's see what is the average value. So this is the waveform we are getting at the output. For this waveform, time period is pi year and the area of conduction is 0 to pi. Okay, and the average value formula is area of conduction divided by time period. Okay, area of conduction divided by time period here. So if you see the average value is equal to area of conduction is from 0 to pi, and it is, as it is a voltage waveform, V into d omega t with respect to d omega t divided by time period is pi. Okay, so we know the instantaneous value formula, V is equal to, so since we know that V is equal to Vm sin omega t. So if it is a current waveform, I is equal to Im sin omega t, we will get. So as it is a voltage waveform, V is equal to Vm sin omega t. I am replacing V by Vm sin omega t d omega t divided by pi. Now I am separating Vm by pi separately, Vm by pi, and the remaining term 0 to pi sin omega t d omega t. Here from this we can say that integration of sin omega t is minus cos 2 omega t. Since integration sin omega t is equal to minus cos omega t. This is a formula we have. That's why integration of sin omega t is replaced with minus cos omega t. I am taking the limits 0 and pi, 0 to pi. Now apply the limits here. Vm by pi is as it is, and minus of cos pi minus cos 0, upper limit minus lower limit. Okay, now if we write the value here, what is the cos pi value? Since we know that cos pi value is equal to minus 1 and the cos 0 value is equal to 1. Okay, cos 0 is 1. Now replace this value with the minus 1 and 1. Cos pi is replaced with minus 1 and cos 0 is replaced with 1. Here minus 1 is minus 1 minus 2, minus 2 into minus plus 2. So here V average value is equal to 2Vm by pi. So average value of the bridge full wave rectifier is 2Vm by pi. Okay, now let's see the RMS value. Root mean square value. So this is the average value we got here. Average value is equal to 0 to pi Vm sin omega t d omega t by pi. So root mean square means for this average value, for the mean value, we have to take the root as well as the square. So we will get the RMS equation like this. So for the mean value, I am taking the square here. Vm square sin square omega t. Okay, I am taking the root. Okay, so root means square. For the mean value, we have to take the root as well as the square. We will get the equation like this. Okay, so Vrms square, Vrms is equal to, so sin square omega t we will replace with 1 minus cos 2 omega t. To simplify the circuit, we are taking this one. So since we know that sin square omega t, we have the formula is 1 minus cos 2 omega t. Okay, 1 minus cos 2 omega t. So I am separating the term here. Vm square by pi integration 0 to pi 1 by 2 d omega t minus 1 by 2 cos 2 omega t into d omega t. I am separating these two terms. Now apply the limits here. If we take the 2 is common here, 1 by 2 common. In the first term, it is 1 by 2 and the second term also 1 by 2. Now if we take the 1 by 2 common, we will get Vm square by 2 pi integration 0 to pi d omega t minus 0 to pi cos 2 omega t d omega t here. Now if we apply the integration For the integration of d omega t is omega t. I am applying the limits here 0 to pi. And integration of cos 2 omega t, since we know that integration of cos 2 omega t is equal to sin 2 omega t divided by 2. So that's why I'm replacing integration cos 2 omega t by sin 2 omega t by 2. I'm applying the limits 0 to pi. Now, if we apply the limits here, upper limit minus lower limit, we will get pi minus 0. Pi minus 0 minus sin 2 pi minus sin 0 divided by 2 we will get. Okay, now, sin 2 pi value, we know that since sin 2 pi is equal to 0 and sin 0 is equal to 0. So replace the sin 2 pi by 0 and replace sin 0 by 0 here. So this total term 0 minus 0 divided by 2. That's why this total term will become 0. Now, here sin Vm square by 2 pi into pi minus 0. This term will become 0. So here pi get cancelled. Finally, we will get here this square and this root both are will get cancelled. We will get Vm divided by root 2 we will get. So VRMS value of the bridge full wave rectifier is Vm by root 2. Okay. Now V average value, VRMS value of the bridge rectifier is completed. Now let's see about the form factor. Form factor is equal to formula is VRMS by V average value. So as we know, VRMS value of the bridge rectifier is Vm by root 2 and V average value is 2Vm by pi. So here Vm get cancelled. If we calculate the remaining value, we will get 1.11. So form factor of the bridge rectifier is 1.11. From this we can say that VRMS is equal to 1.11 times of V average value. Next, peak factor. Peak factor formula is peak value by VRMS value. So as we know that peak value is Vm and the VRMS value of the bridge rectifier is Vm by root 2. Here Vm get cancelled. So peak factor of the bridge rectifier is root 2. So this is about the form factor and the peak factor. Peak value is equal to root 2 times of VRMS value. Now we'll see. So what is ripple factor? Okay. Now let's see what is ripple factor here. Ripple factor is equal to, okay, ripple factor will be defined as the ripple factor is defined as the ratio of RMS value of the AC component to the DC component. The ripple factor functionality is to explain the how much amount of AC ripples present along with the DC output. Okay, now here if you see the formula, ripple factor is indicated by gamma here. Gamma is equal to VAC by VDC. Okay, from this ripple factor, we can say that in the output DC, there are some there are some ripples. Okay, how much amount of ripples present in the output DC, that we will find out by using this ripple factor. Ripple factor formula is ripple factor is equal to VAC by VDC. Okay, VAC we can write it as VRMS square minus V average square. Now, if we write the ripple factor formula, ripple factor is equal to VRMS square minus V average square divided by DC. We will write in terms of V average square. Now, if we take V average to the inside, we will get VRMS square minus V average square divided by V average square. So here I am writing ripple factor is equal to VRMS square divided by V average square. VRMS square divided by V average whole square. Here square here V average whole square minus here V average square divided by V average square is 1 minus 1. Now substitute the values here. VRMS value we got Vm by root 2. Vm by root 2 whole square divided by VRMS value we got 2Vm by pi whole square minus 1. So here Vm square get cancelled. If we calculate the above value, we will get 0.48. So ripple factor of the bridge rectifier, we will get 0.48. Now if you see the efficiency, so efficiency is the ratio of output DC power to the input DC power. So if you write the efficiency is indicated with eta, eta is equal to output power by input power. Okay, output is DC, output DC power by input AC power. Okay, into 100. Okay, here output we will output DC is average square into I average square into RL. As we know, the power formula is I square into RL. I square average RL, and the AC is I square RMS IRMS square into RL. Okay. Now, if we substitute these formulas in the efficiency equation, we will get efficiency is equal to I average square into RL divided by IRMS square into RL here. Okay, yeah, RL get cancelled. So efficiency is equal to average value. We know that that is I 2IM by pi 2IM by pi. Sorry, here it is 2IM by pi whole square divided by IM by root 2 whole square. Here IM square get cancelled. So here we will get finally 4 by pi square into 2 into 100. Here we will get efficiency is equal to 81%. Efficiency of bridge rectifier is 81%. Now if you see the transformer utilization factor is a ratio of power DC by power AC of secondary winding. Okay, secondary winding, at the secondary winding we have to calculate the power PDC divided by PAC of secondary winding here. Now if you see the formula here, I average whole square into RL divided by, so power we will write in terms of RMS value, IRMS into VRMS value. As we are taking the power at the secondary winding of the transformer, that's why we are writing in terms of IRMS into VRMS. Okay, now we'll see I average value. We know that I average value is 2IM by pi whole square into RL divided by, okay, IRMS value is IM by root 2, and VRMS value we can write it as V is equal to I into R, IRMS into RL. Since we know that VRMS value is equal to IRMS into RL, okay, into 100 here. RL get cancelled. Okay, here IM square get cancelled. Here we can write that 4 into RL, 4 by pi square. Yeah, RL already it is cancelled, so no need to write. Okay, here divided by, yeah, IM already it is cancelled. That's why here we have to write 1 by root 2 into IRMS value is IM by root 2. Okay, here one IM will be there here because it is IM square. IM only cancelled. That's why only one IM is there here. IM get cancelled. Finally, we will get here 4 by pi square. 4 by pi square. Here root 2 into root 2 2 into 2 into 100. So transformer utilization factor is equal to, we will get 81%. Okay, so this is about the transformer utilization factor of the bridge rectifier is 81%, and the efficiency also we got 81%. Now let's see the peak inverse voltage. Peak inverse voltage, this is the maximum value of the reverse voltage which the rectifier has to withstand during the non-conducting period. So we will calculate the peak inverse voltage at the when the diode is in reverse bias. Across the reverse bias of the diode, there is a voltage exists. That voltage is called as a peak inverse voltage. That voltage we have to calculate. Okay, if you see the circuit here, I am taking the negative half cycle of the circuit here. Negative, and it is a VI. Okay, it is input is AC. Input is AC. It is a negative terminal and it is a positive terminal. Okay, if you see the component circuit equivalent circuit here, it is V gamma. Okay, and it is a negative terminal and it is a positive terminal. It is a V naught and it is a RF. It is V gamma and it is RF. So this is not RF, it is RL. Here, this is called as RL. Okay, across this open circuit terminal, there is a voltage exists. That voltage is called as the peak inverse voltage. What is the VD? We have to calculate here. Okay, so in this loop, so you can apply the KVL in this loop, or you can apply the KVL in this loop, because in this loop also there is an open circuit. Here also there is an open circuit of the diode. As it is open circuit at the downside, I am applying the KVL here. If we apply the KVL at this side, we will get apply KVL. Apply KVL. If we apply KVL, the equation we will get -2 plus VD and -2 plus V naught, and here -2 plus V gamma is equal to I of t into RF here. Okay, so the -2 plus VD, -2 plus V naught, -2 plus V gamma is equal to I of t into RF. As we know that in the ideal case, V gamma and RF is equal to 0 in the ideal condition. So we have to substitute that VD plus V naught. This V gamma is 0 and it is RF is also 0. So here we will get here VD is equal to minus V naught we will get. Okay, as we know that V naught is equal to VA. We know that V naught is equal to VA. Okay, so VD is equal to, so we will replace V naught with VA. So we will get VD is equal to, as we know that VA instantaneous value is equal to Vm sin omega t. VD is equal to Vm sin omega t. Since we know that instantaneous value VA is equal to Vm sin omega t. From this we can say that this negative indicates the inverse value and this Vm indicates the peak voltage. So peak inverse voltage of the bridge rectifier is Vm. Okay, this negative value indicates the inverse voltage and this Vm indicates the peak voltage. The peak inverse voltage of the bridge rectifier is Vm. So like this we will calculate the peak inverse voltage. Now if you see the summary, V average value we got 2 Vm by pi, and the Vrms value we got Vm by root 2, and the form factor we got 1.11, and the peak factor we got root 2, and the ripple factor we got 0.48, and the efficiency we got 81%, and the transformer utilization factor also we got 81%, and the peak inverse voltage is Vm. So this ripple factor is good, 0.48, and the peak inverse voltage also Vm it is good, and the efficiency is 81%, it is also good, and the transformer utilization factor 81% is also good. So this bridge rectifier is having all the advantages compared to half-wave rectifier and the center-tapped full-wave rectifier. In the center-tapped full-wave rectifier is also having all the advantages except peak inverse voltage. Here the peak inverse is also we are getting Vm. This is also advantages. So these are all the advantages of bridge rectifier compared to center-tapped full-wave rectifier and the bridge rectifier. That's why we use the bridge rectifier practically. Okay, this is about the bridge rectifier. Thank you everyone.